but it's okay. I mean, this is a process of learning, so I kind of hope there's going to be revisions. Honestly, the fact that there's revisions makes me happy because it means you didn't have ChatGPT do it for you. So it's like, yes, you're trying, thank you. I just want your honest, most realness, and we'll get there. So, cool. There was this one problem, I think it was the second problem. So first off, on that first problem with all the various sets, and you had to find upper bounds and lower bounds. On that one, I need a little bit, like, when you have the set, almost everybody did this. You just put the set down, almost everybody, but not everybody. You know, you had some crazy set, like, I don't even remember, you just got some crazy ass set like that, you know, whatever, and then n equals blah, blah, blah. And then folks were like, upper bound is 3 and the lower bound is 0, and it's like, I don't know if that's obvious. So like on that one, I'm gonna make you rewrite this. Like, what does the set look like? Can you just show me we're not just randomly guessing at what the set looks like. So probably there's gonna be some rewrites on that. That's easy, right? Just show me the set. But this one is the one that I was starting to just write a lot on folks' papers, and I wanted to talk about it. So we had set S is a subset of T, and we were asked to show this. Remember that one? Yeah. So I'm not sure anybody's completely got this one right yet, and that's cool. But I want to talk about, I'll talk about this part, and I think everybody's going to end up having to redo this. So that's cool. That's all good. Like I said, all good. So let's just talk about this bit first. So basically, there's 3 things to prove here. First, you're going to prove this inequality. Then you're going to prove this inequality. This one's the easiest here, but it needs a little more than what I'm seeing. And then we're going to prove this one almost identically to this one here. So I want to show you how to approach this one. This one, maybe we can talk about on Wednesday when I give them back. And then this one, you'll just kind of mirror this. So 3 inequalities to show. And I'm putting this up here for Liv to check out as well. So let's just first show this inf t is less than or equal to inf s. So a little proof for that. So we know this. And one of you, and Christian, I think it might have been you were kind of like talking this through, and I could see you were thinking it through, but the words are too imprecise. So we got to get a little bit more precise in the language, and especially with like the inequalities, and that's kind of the hard part of this, the getting the precise part. So we know this, yeah. And we know that inf of s is a lower bound for t, for s, sorry. S, it's the greatest lower bound. So it's definitely a lower bound. So one of the things I think to keep in mind is you want to argue, you want to pull back from these things being the least or greatest lower bound, upper bound, and just think of them as bounds first, and then argue why they have to be the greatest or the least in that way. So we know that inf t is a lower bound, just writing out what I know, for t. Since everything that's in S, and Camille, you were kind of arguing from this perspective. You're saying everything that's in S is in T. Totally true. But that means that inf S, since it's a lower bound for T, it's also a lower bound for S. So, and since S is a subset of T. Everything that's in S is in T. Inf T is a lower bound for S as well. So let me stop there, just check that out. Notice just very subtle, very slow movements. So at this point now, I've kind of related the infimum of T to S. This is the link to get us talking about S. Just noticing that this is a lower bound. But inf S is the greatest lower bound. Let's put LB for S. So I know that this is a lower bound for S, but this is the greatest one of them all. So they must have this relationship that the inf of T must live to the left of inf S, because this is the greatest lower bound on T. So check this out. I said inf T is a lower bound for the set S. But this is the greatest lower bound for S. So therefore they must sit in this relationship. Just and tell me if you need more words, tell me. I just want to make sure. Yeah, ask.
I don't understand how you're making the jump from those two. Like conceptually.
Yeah, no, good.
As far as like the proof goes, I don't really understand how you're able to like just draw that connection.
Cool. Okay. So if I said to you, let's kind of pull some things out here. If I said that M is a lower bound for S, let's just forget about the other. I can think the inf is what the inf T throws you off. How does M relate to S, inf S? So how does this M relate to the infimum of S? What is the definition of this? So like let's talk it through. Greatest lower bound, right? So this is a lower bound also. Here's another lower bound. But this is the greatest. The greatest of all lower bounds.
Oh, okay.
You see?
See?
Yeah. So it must be bigger than this other lower bound.
That makes more sense.
Does that make sense? Do you see that? And it's I think pulling this, getting inf T out of there got it kind of away. So let's look, how did I argue that inf T was a lower bound for S? Because I know that inf T is a lower bound for T, and I know that everything that's in S is also in T. So any statement that I make about lower bounds for T must also apply to S. So since S is inside there, everything that's in S is an element of T, then inf T is a lower bound for S. And I'm not saying it's the greatest lower bound or anything, it is just a lower bound for S. And maybe I can write this out, make this a little bit clearer, because I'm not sure I totally believe that either. So we know that infimum of T is less than or equal to T for every T in T. Let's write that out. Every S in S is also an element of T. So that means that anytime if I say this must also apply for every S in S. So therefore, infimum of T is less than or equal to S for all S in S. Because all these guys are in T as well. And then this is the tricky part here. So let's think about, let's actually maybe take it right now. I kind of want to leave this middle one for separate work. Right now, can you do the proof of this? Let's just write it out right now. Let's take the time to mimic this rhythm and do it there. And then we have it on paper, then when you get your revision, it'll be pretty much done. But I think it's important that we talk about it. So yeah, so what I'm asking you to do now, and Lev, do this with us, is I want you to show that if S is a subset of T, then the sup of S is less than or equal to the sup of T. And it's gonna mirror this. It's not gonna be the exact flow with the S and T. They're gonna flip roles. And Cormac, I have no idea what you did here. You might have got it, but are you feeling like it probably wasn't?
Yeah, I definitely did not do it that way.
Cool, cool, cool. There might be other ways to do it. I don't know what they are. I'm not saying you didn't get it.
Yeah.
Good. You're not putting money down on it though.
I
Yeah,
think
okay.
so.
It's like elegant in a way. It's just hard because it seems, it's also subtle.
The way I was doing it definitely felt like I was just brute forcing my way through, like.
It looked painful.
Oh my god, it was so long.
There's a lot of words.
So
Yes,
many
it's
words.
okay. It's okay. Yeah, yeah. And you know, if you're waiting, just really quick, how do we know? How do we know that? Let's take a minute on that. I just wanted to make sure everybody had a chance on this guy over here. Let's maybe talk about it. Camille, I was kind of waiting to make sure you were finished right. Are you good? Yeah. Cease, you good on this? Somebody want to walk me through this? I got us started. We know. Let's get a proof. We know. What's next?
So then S is an element, or is the set S is a subset of T.
Yeah, good. And also, by the way, everybody's doing great with the language and writing things out, so thank you. I really appreciate it. There's no complaints about the words. There's a lot of words sometimes, but it's cool. I take more words than less words. So, and also, S is a subset of T. So then what, Camila?
So then supremum of S is an upper bound for T?
Supremum of T.
Oh, yeah.
Yeah, cool. Is an upper bound for S, yes. And then what, how do we take it home?
But the supremum of S
Mhm.
is the least upper bound.
Yeah. So, what's the last line?
So the supremum of S is less than or equal to the supremum of T.
Absolutely. Yeah. Beautiful. Beautiful. So now we got two halves of this, right? Almost same thing, mirror images of each other. But now we got this last little beast that we want to talk about. Let's clear this up. Boards this semester. So let's see here. So this is just like S all to itself. What can we do here? We don't want to say that this is obvious. Because it kind of feels like it, but I don't know if any of this stuff's obvious. So we got to make sure S is not empty, I think. That's probably true. So what can I say about an element? So for any S in S, it's not that much. There's just one little line we kind of need to get in here. So for any S in S, I just want to pick one of these guys out of S to have as an anchor. What is bigger than that S? Bigger than or equal to it? Now, so don't think too deep, but supremum. Because that's an upper bound on all these things. And then what lives to the left? The infimum. So, and I would say here, because inf S is a lower bound on S, and sup S, and maybe this would go ahead of this, is an upper bound. And so notice here, I'm not even talking about them being the greatest or the least. They just are bounds on the set. This is an upper bound on S. We're not even invoking the leastness or the greatestness. So this just comes about because lower bound and upper bound. That's it. And but then these link them to the left and right inequalities. So a little surprising there. So it's kind of like what you were saying, Christian, but it just needs that extra little, like I said, this anchor here. Yeah.
I think that when I was doing it, I tried to split it into like two cases where you'd have, where I was trying to think of
Equals
it as, like,
and
two
then
cases,
greater than,
exactly.
yeah.
Or like it'd be a set with one element, and like the infimum is like the set
Yeah.
is the supremum, and then the set with multiple.
These things generally get super painful in cases,
Yeah.
as you found out, right?
Yeah.
Yeah. So it's really just like 2 or 3 lines tops. Yeah. Whole proof. Tiny. We feel better about that? Does that feel good? So then when we get those back on Wednesday, we kind of know how to proceed on that. I'll probably just wait to give you a new assignment on Wednesday. Well, I don't know. I guess we could have a few things to start working on. That might be good. Let's talk first and see what we get to. We're going to talk about sequences. So I think this is chapter 2 in our book. And And if you just want to start reading, that is what I recommend. Just start working through chapter 2. I would highly recommend reading up. This actually might be your homework for Wednesday, because I don't think there's anything outstanding right now. Read pages 31 through up to 42. So that's actually just section 6, so 2.7 and 2.8. So how that works? Yeah. Yeah, just like that. This section here is a lot of what I'm going to talk about today. This just will give you tips on proving things, which I'll also talk about today. We're going to do a little warm up, start warming up on that. So sequences, lists of numbers, that's what they are. A sequence of real numbers. And there's lots of different notations. Our book uses this notation, S sub n, in parentheses like that. Sometimes we tell what the range of S is. Sometimes we just don't, it doesn't matter, and we don't put anything here. But what this generally implies is a list of numbers, is a list of real numbers. And so it's going to go S1, S2, S3, on down. An infinite list. Let me be more precise there. So all our sequences will go on forever. So this is a list of numbers and never stops. And there's lots of ways to express this. So we might just get the list. We might get a formula that looks like this. I might get -1 to the n plus 1 over n. And maybe no indices. Maybe I just get this. So examples. I give you this. That means you kind of just have to pick, where's this going to start? Probably 1 is a good spot here. So I'm just going to put a little note here. Assume that n equals 1 is the first, if not given, which is probably a good thing to do. And what this means is I've got a list here that's going to look like this. It's going to be -1 to the 1 plus 1 over 1, comma -1 squared plus 1 over 2, -1 cubed plus 1 over 3, dot. And then I would simplify that. And I would be very explicit about this. Let's practice writing out things for ourselves and for me. So that first one's just 0 over 1. That next one is 1 over 1. This next one is 0 over 1. What's the next one? What's the next one in the list?
Is it 1/2?
Yeah, exactly. How'd you get that, Corbin?
-1 to the 4th is 1, plus
Yeah.
1 is 2, over 4 is 1/2.
Beautiful. So it's 1/2. 2/4. Perfect. And then you can kind of get the rhythm. Next one's going to be 0. Next one's going to be whatever it's going to be. It looks like we're hitting the evens here. So it's either a 0 on top or a 2 on top. So the next one's going to be 0, and then the next one's going to be 2/6, aka 1/3. Does that sound okay? We understand how to follow the rhythm with that. And then that just goes on and on. Now, one of the things I'm going to highly recommend you do when you're thinking about a sequence is to make a picture of the sequence. This is going to get you so much insight that it's hard to get by just looking at a list of numbers. And in fact, we're going to think about it from the proof stamp. It's going to help us understand proofs as well. So I recommend making an image where the terms of the sequence are up here. So this is going to be S sub n, and this is going to be n. So here's n equals 1, and n equals 2, n equals 3, n equals 4. So for this sequence, it might look something like this. S sub 1 is 0. S sub 2, so this is S1, this is S2, is 1. I'm going to put that up here. So that's S2, that's S1. S3 is back down to 0. S4 hits a half, so there's a half. And then I can get this nice little picture that helps me just get the rhythm of this thing. Next one was a third, and then on down. Definitely helps see what the heck is happening. So let's take a look at a few others. What about this one here? Let me see what you can, you might want to get your calculator out. I know we don't use calculators. And let's start at 1 to infinity. What does that sequence look like? Or maybe you remember nice cosine values, and that'd be exciting. Warm my heart. You know what, let's not just write out cosine of pi over 3, cosine of 2 pi over 3. Let's see if we can get those precise values. And understand what this sequence might be doing as we move to the right. Let's keep the calculators out because I got a couple more. Definitely get a picture going. Kind of spin it around the unit circle. I don't know if you're unit circle folks, how that works. I have to rebuild this stuff with SOHCAHTOA every time I do it, which isn't a bad thing. It's good to know SOHCAHTOA. So what do you all think in the sequence does? Yeah, what are the precise values that come out?
It would be like negative, or 0.5, negative 0.5, negative 1, negative 0.5, and then just like repeats.
Nice, yeah, that sounds, are we all kind of getting that, like either with calculators or with this? Yeah, let's just take a look, and we can see the cyclic nature in this picture. That's what I kind of like about it. So cosine is equal to adjacent over hypotenuse. This is a 30-60 triangle. That's the 60. This radius is 1. So the opposite side is the big one in a 36. If this is the 60 and this is the 30, and then this side's a half. So as Cormac said, the cosine of pi over 3 is adjacent over hypotenuse 1/2. So our first value is 1/2. Next value is, we can just use the symmetry of the situation. This is really just this flipped over. So this is negative 1/2, that adjacent side. And then when I come down here, this is, oh wait, I missed one, didn't I? Yeah, we hit this next one. We hit pi. Cosine of pi is just -1. Can't do that with the triangles. For that one, I always have to kind of fall into this picture here of cosine, which is another good thing to have it ready. Cosine of pi is -1. And then we hit, symmetrically, we're going to hit +1/2. Oh wait, am I getting it? No, sorry. -1. Is that -1/2 again?
Yeah.
Yeah, okay, got it, cool. -1/2. And then we hit this one, which is +1/2. And then we hit 2 pi, which is 1. We're back to the cycle beginning. And then this just repeats again, all that again. So it's kind of a weird cycle, but Cormac gave this little finger wave, and that's exactly what this thing's doing. Let's just take a look at this version of the picture as a sequence. So here's cosine of n pi over 3. So max is 1, min is -1. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to go past a full period. So here we're at 1/2. Here we're at -1/2. Here we're at -1. And we're just sampling that cosine curve at multiples of pi over 3. And then we're back to 1/2. And then we're at +1/2. And then we're at 1. And then we're back here. And seeing these cool little triangles just appear above and below alternately forever and ever. Got one more for you. You're gonna need your calculator. For sure you're gonna need your calculator on this one. So let's take a look at this sequence. I'll write it a little differently. It's the sequence a sub n, where a sub n is n to the 1 over nth. What does that sequence do? You probably saw this in Calc 1 like a billion years ago. It's kind of a pretty sequence, so I just wanted to look at it. definitely gonna need help on some of these values. So what did you get for, did you do keyword at 3 yet?
Yes, okay.
Okay, cool, thanks. What was the next one you got there?
1.414.
Huh, I guess actually that makes sense. It's like basically square root of 2 again. Yeah, huh. Camille, did you get the 5 to the 1/5 yet?
5 to the 1/5 is 1.379.
Ooh, okay, now we're starting to change. Cool, this is very exciting. Anybody got 6 to the 1/6?
1.34801.
Like that, yeah. Start making a little picture. It's pretty weird, for sure. See if you can get a sense of kind of what's happening long term. 'Cause it's very odd. And maybe somebody could just like do the 100th root of 100. We just like, let's just reach way out. We're getting very tedious. We're kind of interested in what the heck is this thing doing? So what is A100?
It's 1.0471213.
Awesome. All right, that was fun, soothing to do these computations, fun to see what's happening. But when we look at this, it goes up, and then it starts going down, and it looks like, doesn't necessarily mean it's true, but that way out here at n equals 100, it's got close to 1. So if I bring this 1 across here, it's getting close to 1. Seems like it's above 1. So we might reckon that this thing goes up a little bit and then starts to decrease and perhaps gets closer and closer to 1. Now I will tell you that the limit of this is 1. If you went back to your old calc days, let me just show you how you would have done it in calc, and then we'll talk about how we're going to do it in real analysis. So if you were to find a limit like this, you would say, oh, let's see, okay, so L equals the limit of n to the 1 over n. And that's really hard to do because you got 2 moving pieces. This is infinity to the 0, essentially. It's an indeterminate form. You gotta take the natural log, and then we're gonna have to L'Hopital that stuff. So what we're actually gonna find is the natural log of the limit, and then undo that. The natural log of the limit, this is a little cheesy what I'm doing here. I'm just pretending I can bring that inside there, and I can. It's totally cool, but in grad school you would have to justify such a thing. So then limit as n goes to infinity, bring the exponent out front. And now I've got this fraction right here. Natural log of n over n. What's that doing? What's the top doing? What's the bottom doing as n goes to infinity? What kind of a form is that? Where's the bottom going? Infinity. Yeah, I know everybody's afraid to say stuff, but it's just infinity, yeah. What happens to natural log is the thing you're taking the natural log gets bigger. Here's natural log looks like that. So what happens? What's happening? Thank you. That sounded very confident, and it should be. Awesome. So that's an indeterminate form too, but I can L'Hopital that stuff. So I'm going to apply L'Hopital's rule, and I get limit as n goes to infinity. What's the derivative of natural log of n with respect to n? Yeah! Oh my god. It was phrased as a question, but it was quite right. Derivative of n with respect to n is 1. I'll take the easy one. Thanks for doing the hard one. What's that limit? 0. Because it's just limit of 1 over n. So we know that the natural log of the limit is 0. So what's the limit?
1.
Yes, exactly. The natural log of 1 is 0. So we can then show that this limit is actually 1 in that way. Kind of seemed like it, but now we know for a fact that it's actually headed to 1. What we're going to talk about for a little while is what does this limit thing mean in a way you've never understood it probably. You probably have a vague sense of what limit is. It's like, it acts like this when I move out here. And that's a pretty good understanding, but we're going to make it better. So let's get very formal. I'll probably stop at about 10:30 and give you 15 minutes for the quiz. You probably won't even need that amount of time. But let's just get an official definition. So, we say that a sequence x sub n converges to L. That's the thing I'm defining. If, here's one of the letters you're going to grow to know well, hopefully not despise in any way. If for every positive epsilon, kind of introduced it gently like last week, it's going to be here all the time now. For every positive epsilon, we can find a natural number, capital N, so that when little n is bigger than that capital N, we have this inequality. We're going to talk about this a lot. X sub n minus L in absolute value is less than epsilon. So let's write that up. That'll be on a quiz in a couple of weeks, along with some other things. So let's take that and rewrite it a couple of ways. So first off, I could make this just more compact. A more compact statement would look like this. For all epsilon greater than 0, there exists an n. And we could put this, if we wanted, in n, such that n bigger than, little n bigger than big N implies x sub n minus L is less than epsilon. So that's the super tight statement. And I'd kind of like you to know both. This is the one that we feel, this is just nicer, works good on our brain, but we're math folk. We need to speak math language. And this is the stuff you show your family when you tell them you're a math major, right? Like, of course, why wouldn't you show them that? So, let's make it a little looser. Let's make that statement have a picture with it. So first off, this thing right here, I want to rewrite this, and I want you to be able to think about this in the following way as well. So this thing right here, on this side This thing right here means that the distance between x sub n and L is less than epsilon. When you have an absolute value, that's actually a double inequality. We don't know if this thing in here is positive or negative. So what it's saying is that it's no more than negative epsilon, and it's bigger than negative epsilon and less than positive epsilon. So let's just write that. Have that there so that you understand that. But then we're going to do one more thing. We're going to add L to all three parts of the inequality. And that's going to say that L minus epsilon is less than x sub n is less than L plus epsilon. We want to be able to move freely here. Make sure that that does make sense. You see how I got from one to the other. Because this is the one that you're going to gain understanding from. You're going to gain a picture in your brain from that one. Let's make that picture. And I'm using different letters for the sequences because we just want to practice not getting attached to any particular letter at all. Pretty much N. We're going to be stuck to N. That's something we're very attached to for the index, but the sequence name can be lots of different things. So let's first make a picture like this, some axes, and then draw a horizontal line about, I don't know, maybe about halfway up that vertical axis. And let's label that L. So that height is L. It's this L here. And then we're going to move up epsilon units. So this little distance here is going to be plus epsilon. This little distance is going to be minus epsilon. I'm going to put a little mark there and a little mark there. And then I'm going to label this as L plus epsilon. And this is L minus epsilon. That's this left bound and this right bound. And I'm going to put straight across from L plus epsilon dashed line, a horizontal dashed line that's parallel to that L line. I'm going to do the same thing across from L minus epsilon. So I've got what I'm going to say often is an epsilon strip. They don't call it that in our book. It's pretty non-regular terminology, but it's visual terminology. And then let's put some sequence points in here. I'm gonna make some 1, 2, 3, 4, 5, 6 hash marks for n, so that's n is 1 through 6. And the first one is gonna go below the bottom dotted line, so that's n equals 1. For n equals 2, it's gonna go above the top dotted line, but get a little closer to it. And then for n equals 3, it's actually going to move up inside that lower line just a little bit. For n equals 4, it's going to be just below the top line, but maybe about halfway in. So it's getting closer to that line. And I'm going to watch this rhythm tighten up. So the next one is going to be below the solid L line, but closer to it. And then for n equals 6, it's going to be above it and super close to it. I got a good picture. Then we're going to label one more thing on here. And then we're going to talk about it. So, notice that for all the indices starting at 3, the dots fall in the epsilon strip. So this isn't in the strip, this isn't in the strip, but from n equals 3 onward. So let's make a little note here, put a little line. From here onward, the sequence falls in the epsilon strip, i.e., and let's put the math behind it. L minus epsilon is less than x sub n is less than L plus epsilon from this point on. So the legend goes, right? We don't really know, because I just made these pictures. This is a picture, we don't have a formula. But we're gonna pretend that's true. So that, this point on, that's the capital N over here. That's the place in the sequence where we start to fall inside the epsilon strip.
You mean lowercase n? Like it's
The big N, that's the big N. So notice here, so for every epsilon greater than 0, we can find a big N so that when the little n is bigger than it, then the sequence values for that little n fall inside the strip. So let me write this out again, because maybe that's still a little confusing. This is important. Thank you for asking. So here, the game is this. You claim limit, and sometimes we'll put n equals, n goes to infinity, sometimes we won't. It's pretty much always implied. X sub n equals L. So step 1 is, I call out an epsilon value and say, show me where the sequence gets epsilon units or less away from L. So I make out a call. I say, here's a strip. Show me where in the sequence this sequence falls inside that strip that I just gave you. And what you're going to give me is this capital N. You're going to say, from this point on, that happens. So 2 is, the response is capital N. It's a call and response game. That's what a limit is. It's a call and response game. It's not a thing that ever is achieved. It's saying that however tight I make this epsilon tube, however tiny I make this tube, there is a place where I will eventually fall into it from evermore. So let me see. The response is N, and from N4, little n bigger than this n, we have x sub n between L plus epsilon and L minus epsilon. So i.e. in the strip. So we have to do this mathematically. That's what a proof is, that this lit is some value. So let's talk about how this is going to roll then. And it has to work for any epsilon. It doesn't really matter what epsilon is. Why don't I have an eraser? Because it's over here. All right, cool. So let me show you how this will work. And we'll start off super chill. Just very chill. So, example. I claim that the limit as n goes to infinity of 1 over n is what?
It's 1. So we,
Slow down.
Oh.
Easy.
0.
0. Yes, sir. 0. Yes, absolutely. It's all good. All good. So I claim this. Here's how the proof is going to go. And you're going to follow these steps. And you're not going to put 1, 2, 3, but let's do it until we get the rhythm. 1. You're actually going to start off every proof like this. We're going to either let or assume that epsilon is a positive number. That's your first sentence. Or let epsilon be a positive number. Then you're going to go do scratch work. Off to the side and magic, right? So in math, we do secret magic, we practice our magic, we bring it back so it looks like a magic hasn't happened, but it is actually some work we do. We're going to do scratch work that we won't include. And what we're going to write out is, now remember, this is, I'm going to pair this up. This is limit as n goes to infinity of x sub n in L. So this is my L, 0. My x sub n is 1 over n. Write out x sub n minus L less than epsilon. So this you're going to plug in, these two things. Plug in your specific values. So here, it's going to look like this. I'm going to write 1 minus n, 1 over n minus 0 less than epsilon. And again, this is my scratch work. Because what I want to do in this scratch work is figure out how big n has to be to fall less than some arbitrary epsilon over here. So I got to do some work, some inequality work. So your next step is, what you're really kind of hoping here, you hope you can get rid of the absolute value. You can get rid of the absolute value. Can I hear, and why? What is true about that little n? What do I know about little n? It's always positive, yeah. It's always going to be a positive number. N's like 1, 2, 3. So this thing is always going to be a positive number anyway inside here. Do we see that? So I can get rid of it. Here we can. Yay. Because 1 over n minus 0 is already positive when n equals 1, 2. So I'm just going to rewrite this inequality like this. Now, how do I solve that for n? I want to get n something relative to epsilon. What's that, Cormac? Yes?
Would you have n less than 1 over epsilon?
Close,
Or do you
close.
have to switch your
Because
inequality?
so when you flip the inequality, and this is like one of the things we practiced early on. So flip both sides and flip the inequality. Yeah, but you had the right idea. You just got to flip the inequality. So keep a note out here when you flip values on sides of an inequality, flip the inequality. And that's gonna happen so much, it's crazy. Cool, I've almost got my answer now. So this tells me about little n, so what I'm gonna say is, from here, we make a choice about big N. Big N is going to be our cutoff. And so what I'm going to do is I'm just going to say, let big N be any natural number bigger than 1 over epsilon. Any one of them. I don't know what epsilon is, but I could figure it out. If epsilon is a 10th, then n has to be bigger than 10. But I need to do this in general. We're not going to pick specific values. N will always be phrased in terms of epsilon. So here's a little thing to keep in mind. That big N depends on epsilon. It's a function of epsilon. We could even put an N of epsilon in the definition of this. So what I would do here is notice that once that happens, so if big N is a natural number bigger than 1 over epsilon, then if little n is bigger than big N, little n fits that bill as well. It follows that. So that's my scratch work. And then we're going to put it together. And I don't know, gosh, I want to give you time for this quiz. I don't think it's going to take that long. Let me just pull it together for you. So step 3 is now that you've done all the work, put it together backwards. Step 3. Your proof is that step 2 work backwards in some ways, and I'll show you what I mean. So here's my proof. I'm going to let epsilon be greater than 0. Then I'm going to pull the magic. Let capital N be bigger than 1 over epsilon. That's what I learned from my scratch work. So this is from secret scratch. And I don't put that, I don't say that. It's a little aside. Then, if little n is bigger than that capital N, we have little n bigger than 1 over epsilon. And now I'm going to have a flow here. I'm going to flip both sides. So I'm going to flip both sides, and that means that 1 over n is less than epsilon. And now I've got to make it look like that L x sub n minus L thing. So I've got to get back to that definition. So keep in mind the goal, here's your little target, is something like this. I need to show that. And here, my target was 1 over n, and that was a 0. And that's going to make life easy. So take this thing here and say that this implies, now I'm going to just subtract 0 from the left side. I'm just writing it out. It didn't really do anything, but I'm moving toward that statement slowly.
Should that be epsilon?
Yes, sir. Thank you. Yep. Thank you. Thanks, Kermit. Yes, sir. And this implies the absolute value. 0 is less than epsilon since n is greater than 0. And we are done. And this shows that the limit of 1 over n equals 0. Same goes to infinity. Tight. But it took some work, and you'll have to, we'll practice this on Wednesday. I think Wednesday is just going to be, we'll get some revisions going, we'll do a few practices of this, and then I'll give you something to do. But what I would just please do that reading before Wednesday. I think it'll help you a lot, especially after seeing this. It's going to make a good gelling in your brain. So let's do the quiz. Just on your own paper, please. Just write out the following things. Archimedean principle. Definition, and I'm skipping some of it, of supremum of S and infimum of S. And here you can just assume S is a non-empty set. And then what does it mean to say Q is dense in R? And what is the completeness axiom?